You ever stop and think about how we get from a tiny little discovery in a lab to, millions of tons of a product? I mean, from the gasoline in your car to the case on your phone, our entire world is built on a massive industrial scale. And the invisible bridge that makes all of that happen? That's chemical engineering. Okay, so at its heart, it all begins with something you probably remember from high school chemistry class. You take a couple of substances, they meet, they react, and poof, something totally new is created. It's the fundamental magic that makes everything possible. And that, right there, is the big problem. I mean, it's one thing to cook up a few grams of something new in a nice, quiet lab. It's a whole other ballgame to produce that same thing safely, cheaply, and nonstop on a scale big enough for the entire planet. That is the great puzzle that chemical engineers have to solve. All right, so let's start our journey where every single great product begins, at the very smallest scale, right there on the lab bench. You can think of a chemical reaction like a recipe. Seriously, you take your ingredients, which scientists call reactants, you apply the right conditions, maybe a little heat, a little pressure, and you get your final dish, the products. The whole goal in the lab is to get that recipe absolutely perfect. And this is where it all happens. This is the birthplace of innovation. A chemist gets that spark of an idea, mixes a few things together in a simple glass beaker, and maybe they create a new kind of plastic, a more powerful medicine, or a cleaner fuel. At this point, it's just pure potential, measured in a few tiny drops. But to turn that potential into something real for the rest of us, you have to scale it up. And let me tell you, that journey from the beaker to the barrel is packed with some enormous, really tough engineering puzzles. And the gap between these two worlds is just immense. In the lab, you're carefully controlling every little thing by hand. In a massive plant, you're dealing with insane pressures, scorching temperatures, and flows of materials so powerful they could fill a swimming pool in minutes. You can't just build a bigger beaker. It doesn't work that way. You have to totally rethink the whole process from the ground up. So this is the multi-trillion-dollar question, right? It's a giant puzzle of physics, chemistry, and economics all rolled into one. And the answer starts with a special piece of equipment that is the absolute heart of any chemical plant. So let's step inside the chemical reactor. This is where that bit of chemistry magic really slams into the hard reality of industrial-scale engineering. Now, engineers basically have two main strategies for this. The first is a mixed flow reactor. Just picture a giant kitchen mixer that's constantly stirring everything together perfectly. The other is a plug flow reactor, which is more like a long pipeline. The ingredients go in one end and travel down the pipe, slowly turning into products, kind of like cars on an assembly line. And choosing the right one, it's absolutely critical. It can be the difference between a successful plant and a very expensive failure. Inside that reactor, an engineer is like a pilot with a super complex control panel. They're constantly balancing all these variables. It's not just heat and pressure. They're worrying about things like mass transfer, which is a fancy way of asking how fast can the molecules find each other to react? And heat transfer, like how do we get rid of all the heat this thing is making? Every single one of those variables has to be controlled perfectly, every second of every day. Just to give you a sense of the kind of scale we're talking about, take a fluid catalytic cracking unit, which is used to make gasoline. One of these units can process 6,000 cubic meters of crude oil every single day. That is enough to fill more than 2 Olympic-sized swimming pools, day in, day out. I mean, that is just a mind-boggling scale to think about. But hey, making the product is only half the battle, because reactions are messy. You get what you want, but you also get a bunch of other junk and leftovers. So now the engineers have a second huge challenge. How do you separate the one thing you actually want from all that other stuff? Well, a lot of the time, it's done in these gigantic distillation columns. Some of them are literally dozens of stories high, like skyscrapers for chemicals. Inside, a hot mixture rises up. As it climbs, the stuff with a lower boiling point turns into vapor and keeps going up, while the heavier stuff with a higher boiling point turns back into a liquid and falls down. Each one of those trays is like a little filter, giving the molecules another chance to sort themselves out with amazing precision. And the result is pretty remarkable. Take a look at this. You can start with a complex gunk from a refinery called reformate, and through this separation process, you can pull out these super pure chemicals like benzene, toluene, and xylenes. Now, these might just sound like random names, but they are the literal building blocks for everything from plastics and paints to medicines. It's the art of creating valuable order out of chemical chaos. So now we've got the key pieces, right? You've got the reaction and you've got the separation. So let's zoom out and see how these fit together to create a modern chemical plant. From a 30,000-foot view, the logic is actually beautiful and simple. You feed your raw materials in, they react, you separate and purify the results, and you get your final product. This simple little loop is the blueprint for thousands of processes that make our entire world work. But simple in theory becomes incredibly complex in the real world. This is an actual diagram for a process that makes something called cumene. It's a key ingredient for plastics. Now, you don't need to understand every single line on there. Just take a second to appreciate the insane intricacy of it all. Every single pipe, every valve, every heater, it's all essential. And that really gets to the heart of it. A chemical plant isn't just a collection of machines. It's a single living, breathing system. It's like a symphony of pipes and reactors all working in perfect harmony, managed by complex control systems to keep it running safely and efficiently 24 hours a day. And that brings us right back to where we started. At its core, this is what chemical engineering is all about. It's the science of taking that one little discovery in a glass beaker and figuring out how to make it available, affordable, and safe for billions and billions of people. So just for a second, look around you, right now. The clothes you're wearing, the screen you're watching this on, the materials that built the room you're in. When you really start to see the world through this lens, you realize the question isn't, what does chemical engineering touch? The real question is, what doesn't it touch?